I'm really pleased to welcome everyone here today. I'm Peter Lowen. I'm one of the associate directors at the Schwartz Reisman Institute, and I'm also the director of the Monk School in the Faculty of Arts and Science. And really pleased to be moderating this talk today by our distinguished guest, Ariel Procaccia. Ariel is a professor at Harvard University. He's recently moved there, coming from having come from Carnegie Mellon, where he began in 2011, excuse me, after a postdoc at Harvard and some time with MIT in Israel. And he received his PhD in 2009 from the Hebrew University of Jerusalem. Ariel's talk today is on democracy and the pursuit of randomness. He's going to talk about an idea that I'm very interested, very happy to be here today, because I'm very interested in the idea of representation through random draws of people, or sortition as some people call it. And it's an idea that is extremely old, of course, but because it's old does not mean that it's well refined. So Ariel has got some very interesting insights about how to think about, I guess, how to optimize sortition given the competing goals that it's trying to achieve. So Ariel, I'm not going to say anything more because you're the expert, but I just wanted to say welcome very much to the Schwartz Reisman Institute. We're very much looking forward to this talk. I feel very lucky to be moderating it, and I look forward to turning it over to you. One piece of housekeeping, colleagues, is that Ariel's happy to take questions throughout the talk if you put them in the virtual chat or put your hand up there. So I'll, with those ground rules in place, Ariel, I'll just say welcome to Schwartz Reisman, to Toronto, and the floor is yours.
Thanks so much, Peter. I'm very happy to be here. So let me just go ahead and share my screen. Okay. Good. So now I'm seeing everybody's video. So if you raise your virtual hand, they should be able to see you and call on you if you have any questions. Okay, so the title of the talk is Democracy and the Pursuit of Randomness. And this is joint work with Bailey Flanagan and Paul Gueltz, who are my students at Carnegie Mellon University, Anupam Gupta, who is a professor at CMU, Brett Hennig, who's the founder and director of the Sortition Foundation, and Greg Keeney, who's my student at Harvard. So let me start with this quote from Jean-Jacques Rousseau, who had this to say about early democracy in England. This is the 18th century. He said that the people of England deceive themselves when they fancy they are free. They are so, in fact, only during the election of members of parliament, for as soon as a new one is elected, they are again in chains and are nothing. So this is a pretty dramatic quote, but I think it still resonates with us today when we think about some of the issues facing democracy. But of course, the question is, what is the alternative? Is there a different way of doing democracy? So one possible idea is the idea of sortition, which is democracy built on lotteries instead of elections, or in other words, the idea of choosing representatives at random. Now, this may sound crazy, but as Peter said, this idea actually has a very long history. So it dates back to ancient Athens, where some of the main organs of government were selected by lot at random. During the Renaissance in Florence and Venice and the Kingdom of Aragon, which is part of modern day Spain, again, some of the main organs of government were selected by lot. But sortition essentially disappeared during the American and French revolutions that made democracy synonymous with elections. Today, it's very difficult for many people to think about democracy in a way that is separate from elections. However, sortition made a comeback in the last couple of decades, mainly in the form of citizens' assemblies, which are randomly selected groups of people from all walks of life that are organized by local or national governments and are basically convened to deliberate and reach decisions on important issues that inform policymakers. Now, this has been happening on a wide scale around the world. For example, the Sortition Foundation, who are our partners in this work, organize a couple of dozen assemblies every year around the world, and they're just one of many organizations working in this space. So let me just give you a couple of examples of citizens' assemblies from the last couple of years. A famous one happened in Ireland in 2016 and then again in 2019. These were national assemblies that talked about constitutional issues and led to referenda that in turn led to very significant constitutional changes. So this is considered a huge success story in Ireland. In France, starting in 2019, they had a national assembly to talk about climate change, sponsored by President Emmanuel Macron, with 150 participants. And that's also been quite successful. So, the last estimate I've seen was that 40% of the recommendations of the assembly have been adopted by policymakers. So this has made a significant impact. In Mongolia in 2017 is another example. They had a large national assembly to talk again about the constitution. And as a final example, in Chile in 2020, they had another large national assembly sponsored by the Senate to talk about pension reform and healthcare policy. So these are just 4 examples from around the world, and we'll talk about a couple more examples later in the talk. So what I want to focus on in this talk is the process by which these assemblies are assembled or are selected. Now, ideally, what you would want to do is simply select the panel or the assembly directly at random from the population. So if you want to select a panel of K people, just select K people uniformly at random from the population. However, this is impossible to do because you can't force people to serve on the panel. So instead, in practice, this is the way it works. You again have the population. From the population, you choose a random subset to invite to potentially serve on the panel. I'm referring to these people as the letter recipients because the invitations are typically done by mail with a letter, but some organizations also use phone calls or SMS messages or other methods. So these people are chosen at random. And then some of them opt in, they volunteer and say, I will serve on the panel if I'm selected. And these volunteers form the pool of volunteers. And then we have another random selection step where the panel is selected at random from the pool of volunteers. Now, the problem is that while the set of letter recipients is representative of the population, because they're selected at random, and we want the panel to be representative of the population, the pool of volunteers is highly unrepresentative of the population because of self-selection bias. So let me illustrate this point with an example. This is based on data from Climate Assembly UK, which was a national climate assembly, obviously in the UK, sponsored by the House of Commons and organized by the Sortition Foundation. So here, the number of volunteers was 1,727, by the way, out of an estimated 60,000 invitations that were sent. And the panel size is 110. So you want to select 110 people for the assembly. Now, what I'm showing you here is 7 features that the organizers cared about in terms of representation. And for each one, you can see the distribution of feature values in the population and in the pool of volunteers. So notice that for many of these features or categories, the distribution in the pool is reasonably similar to the distribution in the population. But I want to point your attention to the education feature in the middle. So here there are 3 levels of education. And you can see that people with the highest level of education in green are way overrepresented in the pool compared to the population. And people with the lowest level of education in blue are way underrepresented in the pool compared to the population. Similarly, if you look at the climate feature on the right, so this is position on climate change, where the options are very concerned, fairly concerned, not very concerned, or not at all concerned. And you can see that people who are not very concerned or not at all concerned in red and green have some representation in the population, or a reasonable fraction, but are almost unrepresented in the pool. And this is not surprising, right? Because somebody who's not concerned about climate change is unlikely to agree to spend maybe weeks debating climate change policy. So given this picture, the question becomes, how do we select a panel that is representative of the population from a pool of volunteers that is highly unrepresentative of the population, and doing that at random? So the way organizations typically do this is by imposing quotas on feature values. For example, if you think about the education feature from the previous slide, and remember that the size of the panel is 110, the number of seats that each feature value would deserve out of the 110, if they were awarded proportionally to their fraction in the population, would be 42, 39, and 29 respectively. So what I might do is say, for the lowest level of education in blue, I might impose an upper quota of 45 and a lower quota of 39, for example. So I want it to be between these upper and lower quotas. For the middle level in yellow, I might say it has to be between 42 and 36. And for the highest level of education in green, I might be a bit stricter and say between 31 and 27. And similarly for age, I would impose upper and lower quotas for each one of the values, and I would do something similar for each one of the categories or features. So this is kind of how we can enforce representation in the panel. And that's how it's done in practice. But now the question becomes, how do we select a panel at random from the pool of volunteers in a way that satisfies these quotas? And the way sortation organizations have done that before this work is by using some kind of greedy algorithm. For those of you who are not familiar with the terminology, a greedy algorithm is kind of a standard computer science terminology for an algorithm that's myopic, that in every stage does what looks best right now without looking into the future. So we've seen a whole bunch of greedy algorithms. I want to tell you about, as an illustration, the particular greedy algorithm used by the Sortition Foundation before our collaboration. So I'm going to illustrate it on an example, a toy example. In this example, we have a pool of 20 volunteers that are identified by two features: shape, either star or heart, and color, either green or blue. The panel size is 10, so we want to select 10 out of the 20 people. And in this example, we're only going to have lower quotas. So to keep it simple, there are no upper quotas, only lower quotas. And the lower quotas are 4 on each of star, heart, blue, and green. So we need 4 stars, 4 hearts, 4 blue people, and 4 green people. Now, the way the algorithm works is at every stage, it computes the need for every feature value, which is defined as the ratio between the number of people we still need with that feature value and the number of volunteers remaining in the pool satisfying that feature value. Then it identifies the feature value with the highest need, and it selects uniformly at random from the remaining volunteers with that feature value. So let me illustrate this on this example. Initially, the need for star is 4/10 because the quota is 4 and we have 10 stars in the pool. Similarly, the need for heart is 4/10. The need for blue is 4/11. The quota is 4, but we have 11 blue people in the pool. And the need for green is 4/9. So you can see that the highest need is for green. And then what we do is select uniformly at random among the green volunteers. And I'm showing this supposedly random choice highlighted in the panel on the right. So I've chosen one of the green stars. Now, after making this choice, I have to update the need for green and for star. So after updating, these are the new needs. And based on these needs, the highest need is for heart with 4/10. So the algorithm would choose one of the hearts, which are all blue, uniformly at random, and I'm showing the random choice again in the panel on the right. And now I have to update the need for heart and for blue, so I do that. Again, the highest need at this point is for green, so I choose one of the green volunteers uniformly at random, and I update. The highest need is for heart, so I choose a heart, and I update green, and update, heart, and update, green, and update, and heart. So at this point, I've selected 8 people from the panel based on the algorithm. And notice that at this point, all of the quotas are already satisfied. We have 4 stars, 4 hearts, 4 blue, and 4 green people. So then what the algorithm would do is just select the last 2 people uniformly at random from the remaining volunteers. Now, I want to point your attention to the blue star. right? One of the volunteers is a blue star. And notice that the probability of this blue star of being selected is pretty low. Because remember that what the algorithm did is it chose a green person and a heart, green heart, green heart, green heart. So the blue star had no chance of being selected until the very last stage, where we just chose at random from the remaining volunteers. And in general, the blue star has a much lower probability of being selected than the other volunteers, which seems unfair to this particular volunteer. Now, you might say, well, maybe this is inevitable in this example because of how things are set up. And we'll see in a few minutes that that's not the case. You might also say, well, this is just a toy example. Maybe this kind of phenomenon where some volunteers have a very low probability of being selected doesn't happen in practice. And it turns out that it's, again, not the case. It does happen in practice. So this figure is based on the Climate Assembly UK data that we talked about before. And what it shows is the histogram of selection probabilities of the different volunteers. And in particular, what you are seeing here is that in the lowest bucket of probabilities, they're very close to zero, there are roughly 450 volunteers, or more than a quarter of the volunteers have a very low chance of being selected. Now, you might again say, well, maybe this is inevitable in this example. And again, that's not the case. This is the result of running a different algorithm that for now I'll refer to as the mystery challenger on the same data. And you can see that the lowest bar here is nicely bounded away from zero, which means that all of the volunteers have at least a reasonable chance of being selected when you run this other algorithm on the same data. So the question is, how do we get from the histogram at the top to the histogram at the bottom? And the answer is that instead of running a greedy algorithm, we look at distributions over panels. What do I mean? So let's go back to our toy example. And remember that before I said that you can do something much better on this example. So what I suggest is that with probability 1/2, we'll select the first and third rows of volunteers. And with probability 1/2, we will select the second and fourth rows of volunteers. Notice that each one of these panels satisfies the quotas. Each one has 4 stars, 4 hearts, 4 blue, and 4 green. And moreover, every volunteer has probability exactly 1/2 of being selected under this distribution. So this is great because it exactly equalizes the selection probabilities of volunteers. And intuitively, it's the fairest thing you can do on this example. Well, let's make things a bit more interesting and increase some of the quotas. So suppose that I increase the quota on star to 6, and I increase the lower quota on blue and green to 5 each. Now, I claim that under these quotas, the blue star, which was the most unfortunate in the previous example, actually has to be selected in order to satisfy the quotas. The reason is that if I don't select the blue star, remember that I'm forced to select 6 stars. So that means I have to select 6 of the green stars. But now I have only 4 seats remaining on the panel, and I have a quota of 5 on blue people. So I don't have enough seats to satisfy the lower quota on blue people. So the conclusion is that I have to select the blue star, but subject to that, I have quite a bit of flexibility. And what I propose is that in addition to the blue star, we'll select 5 of the 9 green stars uniformly at random, and 4 of the 10 blue hearts uniformly at random. So this gives us a distribution over many, many panels, each one of which is selected with very low probability. But the crucial point is that every individual is actually selected with very significant probability. In fact, the lowest probability is that of the blue hearts, which are selected with 40% chance. Every time we select 4 out of the 10 blue hearts. And intuitively, this is kind of the fairest thing you can do under the constraint that you have to select the blue star because of the quotas. But this is just one example, and by eyeballing it, we can see something reasonable we can do. What we want is a more general approach that we can apply to any example. And in order to do that, we draw on an area that's very close to my heart called fair division. It's an area that's been around since the 40s and has been explored widely in mathematics and economics and computer science and political science in other areas. And it essentially deals with how to fairly divide stuff according to rigorous notions of fairness. In our case, we think of a distribution over panels of size k as dividing the overall selection probability of k between members of the pool of volunteers. Or in other words, we think of the volunteers as the players, the participants in this fair division problem. And we think of the overall selection probability as a divisible resource to be allocated to the participants. So now that we have this connection, we can use methods from fair division and apply them to our context. And with that, we can now unmask the mystery challenger. It's a mechanism called Lexemen from the fair division literature, which is known to have many good properties in various fair division applications. What it does in our context is it chooses a distribution over quota compliant panels in a way that maximizes the minimum probability any volunteer gets. So making the most unhappy volunteer as happy as possible. Subject to that, it maximizes the second lowest probability. Subject to that, the third lowest probability, and so on. And on the Climate Assembly UK data, it gives the histogram that we saw before. Now, another natural option is maximizing Nash welfare, which is the product of utilities in fair division in general. In our context, it would be the distribution over feasible panels, over quota compliant panels, that maximizes the product of selection probabilities of the volunteers. So this is also something that's known to have nice properties in various fair division applications. And if you run it on the Climate Assembly UK data, it gives this somewhat smoother histogram of probabilities that you see at the bottom, but again, things are nicely bounded away from zero. So everybody has a good chance of being selected. But this is also a nice alternative, but a really big advantage Lexemen has over Nash welfare is that the first thing it does is maximize the minimum probability, make the least unhappy person as happy as possible. And that's something that's very intuitive, that's very easy to explain to practitioners, especially. So it's something that is very compelling to people. And it makes it a more practical objective. So focusing on this objective of, in particular, looking at the minimum probability of any volunteer, you might again say, well, I showed you one real world example where the greedy algorithm does really badly, but it could be the case that on other real world examples, the greedy algorithm actually does okay. So I want to put the last nail in Greedy's coffin by showing you this figure, which is based on 11 different data sets we collected from 6 different organizations that we've collaborated with. So there are 5 data sets from the Sortition Foundation, which is based in the UK, one from the Center for Climate Assemblies based in Poland, one from Healthy Democracy, which is an American organization, Mass LBP based in Canada. They've also been active in Toronto. One from Nexus based in Germany, one from Off-by-4 based in the US as well, and one from New Democracy based in Australia. And so each one of these is an assembly instance, a selection instance of an assembly from a real world assembly. For each one, I'm showing you in purple, K over N, which is the size of the panel that's divided by the size of the pool of volunteers. So this will be the selection probability, the minimum selection probability, or if I could equalize selection probabilities, if I had no quotas. So this is not something that's feasible, it's just a benchmark. In yellow, I'm showing you the minimum selection probability under the Lexemen mechanism. And in blue, you can see the minimum selection probability under the greedy algorithm. And the first thing you'll notice is that in 9 out of these 11 instances, the blue bars are essentially invisible, which means that the lowest selection probabilities are very, very close to 0. And in fact, this is true not only for the lowest selection probabilities, but again, for a good fraction of the volunteers, they have probabilities that are very close to 0. So, this kind of says that pretty much across the board, the greedy algorithm really messes up according to this measure of fairness. Now, a final issue is the issue of implementation and complexity. So these methods that I talked about, both Lexamen and Nash welfare and others, are hard to compute both in theory and in practice. So we have developed a framework to compute these methods. I won't go into the details, but the important thing is that we have implemented it, and it's led to a deployed system called Panelot that stands for panel selection by lot. What Panelot does is it takes as input an instance of our problem, which is the features and the feature values, the pool of volunteers, the size of the panel, and the quotas. And it outputs the Lexamen distribution over quota compliant panels. So this has been around since April 2020, and it was immediately adopted by the Sortition Foundation, who were our partners in this work. So they've used it since then to select all of the assemblies they've done. So, several dozen assemblies, including a national climate assembly in Scotland. But it's also been adopted over these 2 years by many other organizations. And around almost a year ago, we put Panelot online at panelot.org. So it's freely accessible at that address. And now people, now organizations can even more easily access it and use it for their purposes. What I want to show you is one example of a use case of Panelot from a COVID-19 policy assembly that was conducted by Off-Buy for All in Michigan, or I guess it was virtually. So the participants were people who live in Michigan. And again, the idea was to discuss COVID policy. What made it interesting was that they put a lot of effort into thinking about how to make the selection process transparent. And they recorded a video of this show they put around the selection process. So I want to show you 1 minute of this video. I hope I enabled sound sharing. If you can't hear the audio, somebody please tell me and I'll make sure that you can.
So what we set out to do, and what we have done, is sent out invitations to 10,000 randomly selected households across Michigan. Once those of you who were willing and able RSVP'd to us, a volunteer team of computer scientists from Carnegie Mellon University as well as Harvard used an open source algorithm that they developed to generate a list of 1,000 possible panels. Each one of these has a different mix of 30 citizens who again reflect the makeup of Michigan with those proper proportions, women and men, young, old, etc. Now, each of these possible panels is identified now by a unique number, 000 through 999. The three machines that I have here with me, each will select just one digit of that 3-digit number. Together, that will give us a 3-digit number, and that will be the group of 30 that has been chosen to serve as the panel. So what we set out to do, and what we
So that's kind of one example of how to visualize the randomness using lottery balls. Let me show you another example just to kind of illustrate the fact that there are many different ways to do it. So in this example, instead of 1,000 panels, like in this COVID-19 panel, we will have 1,024 possible panels. Each one of them is shown as one of these small blue squares. And we're taking the viewpoint of one of the volunteers and highlighting in red the panels that this volunteer is on. Okay, so each one of these small squares is a full panel, and the red ones are the ones that include the volunteer who's looking at this process. And what we will do is we will at each point spin this wheel of fortune that will tell us to focus on one particular corner of the grid. So the first spin is southwest. So I'm restricting my attention to the southwest corner. Then the second spin gives me northeast. So I focus on northeast. And then we get southeast. And then with 2 more spins, we should be able to get a particular panel, southwest and northeast. So we ended up with one particular panel that happens to be a panel that includes our volunteer. So this is, again, a way of visualizing the randomness from the viewpoint of a volunteer and really engaging people in the process, making it transparent. And notice that for both of these methods, whether you want to draw lottery balls or spin a wheel of fortune, you need to have a distribution over panels. So this is not something you can implement with a greedy algorithm. A subtle point, though, is that you don't just need any distribution over feasible panels. You need a uniform distribution over a small number of panels. What do I mean by small? In one example, we had 1,000. In the other example, we had 1,024. And the idea is that if I have T panels that I want to include, I need the probabilities of the different panels to be essentially multiples of 1 over T. So this is a significant restriction. And you might worry that imposing this restriction would lead to a significant loss in terms of the fairness objectives. But it turns out that that's not the case, that having this kind of transparency doesn't come at the cost of fairness. So we can show this both in theory and in practice. In theory, we can show the following result, that for any distribution over feasible panels of size k, we can construct a uniform distribution over T panels such that each individual selection probability differs between the two distributions by at most k over T. Now, this is good news because remember that we can choose T to be essentially as large as we want. So with 3 lottery balls, we get T equals 1,000. With 4 lottery balls, we would get T equals 10,000. With 5, we would get 100,000. So we can easily make this expression very small. Now, because this holds for individual selection probabilities, it directly implies that the minimum selection probability differs also by at most k over T. And you can also draw similar conclusions for Nash welfare, although you have to work a bit harder. So this is in theory. In practice, things are even better. So if we go back to the 11 data sets we talked about before, like before, I'm showing you in yellow the minimum selection probability under Lexamen. This time in blue, I'm showing you the minimum selection probability under constrained Lexamen, which is Lexamen but constrained to output a uniform distribution over 1,000 panels. And you can see that the blue bars are almost identical in height to the yellow bars, which means that the loss in fairness is extremely small between the non-transparent version and the transparent version. In purple, I'm showing the guarantee, what we get from the worst case theoretical result. And you can see that even this worst case guarantee is pretty substantial. It's bounded away nicely from 0, but still in practice, we get something that's even better and very, very close again to the unconstrained version, which is great news for getting transparency. Okay, good. So the last thing I want to talk about for the last 10 minutes or so is a different viewpoint on the sortation pipeline, which is somewhat more abstract, a bit less practical, but I think is interesting and could lead to practical developments in the future. So the idea is we're going to look at the pipeline a bit differently from a different angle. And let's first denote the size of the population by M. And we'll denote the number of letter recipients by R. And like before, the panel size will be K. So now let's look at a particular person from the population. The probability that they go from the population to the set of letter recipients is R over M, because we select R people uniformly at random among the M people in the population. Now, suppose that we could identify a probability Qi that a particular person, if they got a letter, if they were invited, would accept the invitation and join the pool of volunteers. Remember that before we talked about how this probability in large part depends on various features. So for example, highly educated people are much more likely to accept the invitation. So suppose that we can compute such a probability, and I'll say a few words about this later. If we could have these probabilities, if we could estimate them, what we could do is we could then select people to the panel from the pool with probability that is proportional to 1 over Qi, where Qi is this opt-in probability. If I could do that, the Qi and the 1 over Qi would basically cancel out. And what we would get is that the end-to-end probability of people making it all the way from the population to the panel is K over M, which is what I would get if I could just directly select K people from the population, and I didn't have this issue where people might not opt in and might not agree to serve on the panel. So this, in a sense, implements the abstract, infeasible sortition pipeline that I talked about at the beginning of the talk. So the question is, can we do this? Is this kind of pipeline feasible? And we have some evidence that this might be feasible, both in theory and in practice. So in theory, we can show the following result, that as the number of invitations of letters sent grows, with high probability, it's possible to find a distribution over panels of size K that satisfy the following two properties. So the first property, I think of it as an individual fairness property that says that the individual selection probabilities are very close to the desired K over M. The second group fairness property says that the proportional quotas are satisfied up to a small error. What do I mean by proportional quotas? It's what we saw on, when we talked about quotas initially. It's just the number of seats a group deserves based on its fraction in the population. And this says, that each group will get that fraction up to an error which equals the number of features. In the Climate Assembly UK data, we had 7 features, but typically it's more like 4 or 5. So this says, you can get pretty close to proportional representation of the groups, and that is guaranteed. Now, what is this asterisk in the theorem statement? So this is assuming that the opt-in probabilities are known, and we can reverse the opt-in probabilities as we discussed on the previous slide. This is again a challenge, and we have some evidence that this can be done. Part of the challenge is the fact that we only, for those of you who are familiar with machine learning, if we wanted to learn or estimate these probabilities, we only have positive examples. Only when somebody opts in do we get their data. We don't get their data when they opt out for these negative examples. So this setting is called learning with contaminated controls, and there are methods that you can use to do this estimation even in that setting with the appropriate data. And we show that there is publicly available data that allows us to get accurate estimates of these opt-in probabilities. So I'm not going to go into that. I just want to show you one last result. This result is based on taking real data, so both something called the European Social Survey, as well as the Climate Assembly UK data, using them both to estimate these opt-in probabilities. And then what we did was we generated a synthetic population of 6 million people. And we simulated the process by which you send 60,000 invitations, and people opt in with the estimated probabilities. And then you run one of several algorithms, and you see what's the probability of people in the population making their way all the way to the panel itself. So the graph is showing the selection probability for individuals as a function of their opt-in probability QI. And notice that the selection probability in the y-axis is shown as a multiple of K over M, where K over M is again the ideal selection probability. So 1 is the ideal. Now the blue dots are showing the result of running the greedy algorithm. And you can see that they deviate pretty significantly from the desired K over M. By contrast, the algorithm that's implicit in the theorem that I stated on the previous slide is the yellow dots, and you can see that all of them are very, very close to K over M. And this is encouraging because the theorem is asymptotic. It was saying, as R goes to infinity with high probability, this happens, but this is on a realistically sized data set, and you see that you can get these probabilities that are very, very close to K over M. Now, you might be wondering why I'm only showing the results for the greedy algorithm and not Lexamin. The reason is that Lexamin is too computationally intensive to run in this experiment because you have to run it many, many times. So you can run it on an instance in practice, but for such an experiment, you'd have to run it many, many times, and that would take too long. But we don't expect it to do better in this kind of experiment because the only reason why you get anything at all from the greedy algorithm is the fact that it satisfies the quotas on groups. And Lexamen, we expect, would perform very similarly for the same reason, because it satisfies the quotas on groups, but shouldn't give you something better in terms of these end-to-end selection probabilities. Okay, so let me wrap up with a take-home message, which is that we, the audience of this, you all, can play a role in improving the practice of democracy and potentially in shaping its future. So this sounds pretty corny, I know, but I think it's interesting, especially when you put it in the context of what I used to say a couple of years ago. So if you heard me give a talk a couple of years ago on computational social choice, what I would often say is that it's very difficult to change the practice of democracy, and that the killer app of this field that thinks about computational approaches to voting and democracy is actually helping small groups of people make smart collective decisions. And in particular, in the applied work from a group at the time, including amazing work done by Nisarg Shah, who's now a faculty member at U of T Computer Science and in the audience, what we focused on is basically building platforms to help people make joint decisions, small groups of people. But what I've realized in this project is that we can actually impact to some degree the practice of democracy. And to me, that is very exciting, and I hope it's exciting to some of you as well. So let me just finish with a bibliography, just references to the papers I talked about. So most of the lecture was based on a paper called Fair Algorithms for Selecting Citizens' Assemblies, which is joint work with Bailey Flanagan, Paul Gueltz, Anupam Gupta, and Brett Hennig, and was published in Nature around half a year ago. The stuff about transparency is based on work with Bailey Flanagan and Greg Keeney, Fair Sortition Made Transparent in Europe's 21. And the last part about these end-to-end probabilities is based on work with Bailey Flanagan, Paul Gueltz, and Anupam Gupta. The paper is called Neutralizing Self-Selection Bias and Sampling for Sortition, and it was presented in Europe's 2020. Thank you so much, and I'm happy to take questions.
Thank you very, very much, Ariel. Indeed, this is a very interesting question or talk. I've got lots of questions, but I want to turn it over first to people in the audience. So if you want to raise your hand, John Enman Beach, you are the first with your hand up, and then Nisarg. John, and then we'll, okay. Yeah, John, thanks. Please.
I have a simple clarificatory question. The opt-in probability QI, is that on an individual level, or is that probability that a person who fits a certain category will opt in? And how do you figure that out? If it's the second, how do you decide?
Yeah, so what we do is the probability is estimated based on categories, based on these features that we talked about. And the specific model we use is, it's called the independent action model. So the idea is that you have a product of parameters where each parameter is identified with each feature values. For example, you'd have one for your education level, one for your gender, and so on. And the probability of opting in is the product of these different parameters. So conceptually, the idea is that every feature gives you some reason to opt out, and you kind of have to opt in all of the different features. I don't want to argue that this is a kind of a descriptive model for how people make these decisions, but this is, the idea is that with machine learning methods, you can fit these parameters and get good estimates. But again, the short answer is that ultimately these estimates depend on feature values satisfied by people.
Thanks.
Sarg?
Nisarg.
Hey, wonderful talk. So I have a question. I want to kind of chip away at this underlying assumption that in an ideal world, if we have this underlying population, we just want to select K people at random from the underlying population, if everyone was willing to if everyone volunteered. And so there are, I can think of like some reasons why you may not want this. And I'm sure that you must have thought of other reasons. So one reason is kind of that, yes, we don't want to differentiate between people based on their ideology or what they believe kind of the state of the world is. So for example, taking the climate change example, we don't want to differentiate between people kind of including them in the panel or not including them in the panel based on whether they believe climate change is real or not, or if they believe it is real, how serious of a threat they think climate change is. But what about potentially differentiating between people based on how much effort they are willing to put in or how important that issue is to them? So for example, you can have somebody who doesn't think climate change is real, but is very much willing to put in the effort to influence the policies according to their worldview, or somebody who thinks that climate change is real and is a serious threat in say 50 years, but maybe they just have a very short horizon and therefore they only care about things that are happening this year and they are not willing to put in very serious effort. What do you think about kind of changing that gold standard and potentially thinking of like different factors where people should be differentiated based on that factors? Is that a good factor to change, kind of differentiate people based on? I'm not saying that this is feasible, because if you ask people, are you willing to put in an effort? Anyone who volunteers and who wants to be on the panel would obviously say, yes, I'm willing to put in a lot of effort and select me. So I'm not saying that this is feasible to actually implement, but just kind of conceptually, does it make sense? And are there other factors that you have in mind?
Yeah, that's a great question. It's something I thought about. I even chatted about it with Alexandra Martin this morning about this particular question. So, there are a couple of related issues that you might wonder about. One is, level of engagement. The other is also competence. So that's also something people sometimes say. Maybe somebody who has a higher level of education would be more competent in discussing the relevant questions. So is it should we be worried about high education being overrepresented in the pool? Maybe we should give those people a greater degree of representation. So so I think there is an argument to be made in that direction. But what Alexandra and I agreed on are that there are two, at least two arguments against that I think are quite compelling. So one is from a kind of the viewpoint of political legitimacy. There is a lot of evidence that people view panels that are representative of the population as being more legitimate, because people want to see themselves represented on the panel. So if you have a panel that's more biased towards specific groups that are more engaged or more competent in a sense, then that wouldn't, a lot of people wouldn't see themselves represented on the panel, and that would harm the legitimacy of the whole process. So this is kind of from the, one political theory approach to thinking about this. But then even from the epistemic viewpoint, I actually really love an example that Alex gave. Hopefully it's okay for me to share it. So in the context of kind of work that she did on consulting about AI ethics. So a lot of the people who participate in the consultation are people with an academic background or higher degrees who are already engaged in the space. But that means that the results of the consultation are very similar to what you have, what you get out of academia anyway. And the reason is that you don't have representation from people who have a different experience, and which might lead to outcomes that are different from what we could get on our own. Right? So even from an epistemic viewpoint, it's not clear that you want the most engaged and most competent people to be the ones that are kind of the ones calling the shots or the ones that are engaged.
That makes sense. Thanks for the answer.
Is it Shashank?
Yeah. Hi, it's a great talk. I have one quick question on why you preferred lower bounds, but changing it to upper bounds make more sense, especially thinking about representation of smaller groups. Maybe they might have a higher probability of being selected if they're upper bounds instead of just lower bounds.
Yeah, absolutely. So in practice, practitioners use both upper bounds and lower bounds. The just lower bounds was just for the toy example to make it a bit more, easier to explain.
All right, good.
Nisarg, I'm going to come back to you. I want to ask a question, Ariel, about this. So I have a few things to say. I mean, one is that this, I'm sure you're alive to this, but this has very interesting applications to survey research generally, right? So the problem of survey research now is that it was never possible, but we now realize that doing proper random draws of a population are impossible, right? Used to seem easier when people answered their home phones, but even then we didn't have universal coverage of home phones. So we still have this issue now of a population, people get impaneled into survey panels and they get sampled from that, right? And there's quota sampling at both levels. But I just as a person who does a lot of survey research, I just note that this is a very interesting solution to a very serious problem for people doing population-based research. I wanted to ask you in particular though about citizens' assemblies. So let me push on a couple of elements. One is I just want to hear your reflections on the degree to which this deals with the problem of unobserved heterogeneity in populations according to, for example, their underlying beliefs. So to the degree that that underlying beliefs are perfectly correlated with observables on demographics, then you can deal with this, right? But what if there is something where there's a correlation between what people's preferences are and their willingness to be engaged in a panel? And how do we deal with that with this sampling method? That's kind of question one. And then the second one is, I just ask you to reflect on this. What if what we want is not actually representativeness in our sampling with citizens' assemblies, but what we want is, and this is kind of Nisarg's question a little bit, is something like a willingness to deliberate, and that is the thing that we want. So some particular unobserved trait of people that we're trying to figure out. What's the benefit of this method if what we want to select on might actually be willingness, right, of people to engage in deliberation? Because the conceit of citizens' assemblies, right, is not that. The conceit of citizens' assemblies to me seems to be not that drawing a random population will epistemically give you a good outcome. It's that having a representative group of people leads them to deliberate in a way that leads to single peaked preferences that then leads to a more rational set of decisions, right? So it's not really about the representativeness, it's about the act of people deliberating together, and that may not be actually conditional upon representativeness. You've obviously thought about this much more than me, so I'd love to hear your thoughts on this.
Yeah, definitely. So starting from the point about surveys, I think it's a great point, and it's something I would love to chat about more. I think the one difference is that typically in surveys you don't have an issue of fairness to volunteers, and kind of the main thing in our work is how to reconcile the issue of representation, which is, I believe, the main issue in surveys, with the fact that you also want to be fair to volunteers. So for that reason, it's not clear to me that our contribution to the space of sortition is what would be most useful for surveys. Right, like the
interesting, yeah. I mean, unless the surveys care about fairness in the sense that government's doing consultation, for example, right? If governments want to do a large-scale survey to consult people, they should be doing it in a way that is, I think that it adheres to your notion of fairness. But please go on. Yeah.
So that's kind of one thing to keep in mind. Regarding the unobserved feature, so just to kind of recap the question, it was, we might have some features that we have quotas for, but there might be some other feature that we don't observe, maybe an opinion, a political belief, and what can we say about that being represented? So I have a good answer for this in a slightly different setting, but hopefully it will at least answer your question part way. So our first paper on sortition, before we started working on the practice of it, was about precisely this question. So the kind of setting we were looking at was stratified sampling. So we select, the population is partitioned into groups, and we select from each group proportionally to its size, but uniformly at random, subject to that constraint. So this is kind of a very reasonable way to do it when you can actually select from each group in the population the right number of people. And we can talk a bit more about why that's not practical if you think about groups as vectors of feature values. But so this is kind of one very reasonable thing. Another thing is choosing, if you could, uniformly at random from the population. And what you might worry is that when you do stratified sampling, which is very close in spirit to what we're doing, what you might worry is that you're stratifying over particular features, but then there might be some unobserved feature, like you said, Peter, some belief that we don't know about, and you might, so you would get really good representation in terms of the features you are stratifying over, but really you would do really badly with respect to this other feature that you didn't explicitly take into account. And what we show is that this is essentially not the case, in the sense that if you compare stratified sampling with uniformly at random from the whole population, sometimes when the unobserved feature, like you said, is highly correlated with one of the features we're stratifying over, you can get much lower variance on the unobserved features, so get the right number, something very close to the right number. And you can essentially never do worse than sampling from the entire population. So you can do slightly worse in terms of variance of the number of people from the unobserved group. And we bound how much worse. It's something very small that essentially goes to zero as the instance grows larger. So at least in that setting, we can give guarantees regarding even for unobserved features. When you stratify over other features, you're actually doing quite well, at least compared to uniform random sampling. And we can.
That's interesting.
So this doesn't apply directly to the method they talked about, but it's essentially the same setting where you are kind of taking particular features into account and asking how well do you do with respect to features you didn't explicitly take into account. So this is the second point. For the third point of willingness to deliberate, I don't have a good answer to that. Like, one thing I'm wondering is, again, if you did explicitly take into account willingness to deliberate, whether that would be at odds with things like, legitimacy, right? Like having a representative panel that would kind of look legitimate to people. And I'm worried that it would be at odds, that specific groups would show as being more willing to deliberate, which would kind of be at odds with these other objectives.
Yeah, I mean, I think if I could just follow up on it quickly, I think that the challenge for people who are advocating for open democracy or citizens assemblies or whatever we want to call it is that citizen assemblies are a response to a whole number of problems, right? And the degree to which they're a good response depends on the exact problem, right? So, I mean, to the degree that they're about politicians being in kind of captured by other elites, well, then any citizen should be good enough, should be better than the alternative, right? To the degree that they're about the non-representativeness of the political class, well, then they're then a solution to another problem, right? And I think the optimal research design depends a lot, or the optimal citizens assembly design actually depends a lot on exactly what question you're trying to answer. And for better or for worse, advocates of citizens assemblies don't often articulate exactly what the problem is, because there's a whole bunch of different beliefs about why they're good, right? And we don't really want to push those too far. I don't mean to be critical of them. I think it's just a political reality of how they're structured. Nisarg.
So I had this question, and then I thought that your previous answer about stratified sampling, which is actually a paper that I had forgotten about, answered my question, and then I realized it did not. So I again raised my hand. So this is a bit more technical question, but I was thinking about this individual fairness versus group fairness in your talk. And in some sense, you can think of both of these guarantees as some guarantees on the distribution of what fraction of a group is selected in the final outcome. So for example, the individual fairness, the group can be just one individual. So you can either select a 0 fraction of that group or 1 fraction of that group. And then the probability of selection of the individual is simply the probability that 1 fraction is selected, which basically describes the whole distribution of the fraction of this group that is selected. And for the group fairness, when you're trying to satisfy some approximate quotas, you are basically giving high probability guarantees that with sufficiently high probability, at least this fraction of this group will be selected in the final outcome. So again, this is some kind of guarantee on the distribution of the fraction of a group that is selected in the final outcome. And I was wondering if there is a general guarantee that you can write down, which will apply not only to individuals and not only to these predefined groups, but also to kind of all possible groups to some extent. And I thought that kind of your stratified sampling thing answers this question, because it does actually apply to all groups, but it only gives a guarantee in terms of the variance, which doesn't immediately doesn't immediately imply the individual fairness and group fairness guarantees from this more recent work. And so I was wondering if there is a way to use negatively correlated dependent rounding, essentially, in order to get such a guarantee for all possible groups.
That's a great point. So I think one thing that I think you're definitely seeing is that even the guarantee of K over M individual probabilities gives, says that for each group it would be represented ex ante, right, before the randomness was drawn, like roughly proportional to its size. And one thing to note is that the group fairness guarantee is ex post. You're right that there is a with high probability, but as long as the pool looks like more or less what we expect it to look like, that guarantee is ex post. So it holds regardless of the randomness. So that is a big difference from the kind of guarantee you would get for every possible group ex ante, just from the probabilities being K over M. So essentially, I think what you want is to use the kind of dependent rounding things we do for getting these particular guarantees on quotas for every possible group. My first reaction is that it shouldn't be possible. I don't have a formal proof of this, but that would be my first reaction. Like it feels like a guarantee that's too strong.
Or something that's similar to this, if you know about this fairness gerrymandering paper of Michael Kuntz et al. So something that basically says, yes, you might have a very weak guarantee, if any, for smaller groups, but groups that are either large or groups that are defined by the intersection of a small number of axes. So say women over the age of 55, or men who have at least a certain amount of education. So if you take a small number of intersections of different axes, then those groups would have a good distributional guarantee. And again, I understand that just the ex ante guarantee on the individual selection does give you a lower bound on the expected fraction of a group that is going to be included. But then we want a guarantee that says with at least this much probability, at least this much fraction of the group will be included, which seems like.
Yeah, I mean, that kind of thing you can do directly by defining new features, which are intersections of a small groups of features, right? And looking at all possible feature values. Right. So now you have a much larger number of features, so the errors grow larger. And that's kind of my intuition, that I expect the errors to grow like impractical as you kind of ask for this kind of guarantees.
All right, thanks.
Yeah.
If there are there other questions out there? If not, I've got a couple more, but.
I see there's a question in the chat that just appeared.
Oh, yes, Devansh, just to confirm the representative, who everyone can read. You want to take a look at that? You want to give that an answer, and then we'll go back to Shashank? Yeah.
Sure. Okay, yeah, so the question is, the representations based on quotas, is there work on measuring representativeness, and then how that's related to the feature selection problem of which features are, should we even give quotas on? So I don't know of any technical work on this. For our problem, we accept the quotas as input from practitioners. When people want to put together a panel, they come up with quotas, they come up with features, they come up with quotas. That's an input to our problem. And by the way, sometimes the initial quotas they come up with are too strict, so they relax them. There is some art, in kind of setting these features and quotas. So I don't know if any works. So the short answer is I don't know.
I mean, it seems to me to be a particularly interesting question, right? Because the things you're selecting on, you presume have meaning, right? So you're selecting on gender and age and maybe geography, right? But are you selecting on income or the type of house a person lives in? Or, I mean, there are all these things which are observable features of people, which may matter for deliberation in ways that we don't know, right? And I guess you can recover these through other observable ascriptive characteristics, but there is a certain arbitrariness in the things you're selecting on, right?
Yeah, absolutely.
Yeah. Shashank, and then John.
Hi. So I feel this only applies to the cases where the assumption is that all the participants in a particular sample are the same. But if we use it in cases of like panel selection for like assemblies, or where like the expert's opinion might vary a lot, even if they're from same samples. So like, would it be better than the normal election procedures where people listen to their views and vote on them, or like going with this kind of sampling would be a better approach? What are your thoughts on this?
So you're thinking about settings where I'm not sure I understand what you have in mind. You're thinking about settings where people's opinions differ significantly. I mean, which could be the case here as well.
For the climate change panel, particularly, so we are making an assumption that all the participants from a particular sample represent similar opinions, or like that is the assumption behind it, right?
Not necessarily. So I mean, even on climate change, one of the features that is we want to be represented is position on climate change, right? So that is kind of meant to guarantee that there are people with different positions on climate change, or different levels of concern, at least. So in some sense, the goal in kind of imposing these quotas is to get a range of opinions and experiences. So I think even in citizen assemblies, you do expect and want to get people with very different opinions on the panel.
All right.
John.
Hi again. I think I figured out why I wanted to ask about QI earlier, the opt-in rate, which is I see that you want to pick out of the people who have volunteered, you want to pick them at a rate that is proportionate to the inverse of the opt-in rate, and that intuitively makes it would make the math work out. That makes sense to me. But it's not obvious to me why the estimate of opt-in rate should be based on their membership in a particular category, which is already in the quotas you're looking at, rather than any other way of estimating individual opt-in rates. For example, you might have a gender quota, and that might not correlate with willingness to opt in, but you might also know, education or something that does. And that makes me wonder, though, if there's a good reason to define QI with respect to the quota types you're already looking at, and there might be, and also if there's not a different kind of fairness or representativeness in the chance of you being picked given you're willing, or something like that, that's different from the chance of you being picked as like as a background member of your group.
Yeah, that's an interesting point. So I guess one issue is that the features that play a role in the panel selection are the data that we have. So like when somebody opts in, we basically, we collect data, or practitioners typically collect data only for the features that they then want to impose quotas on. You're saying, maybe there are other features that are relevant. I can definitely imagine a situation where, you would collect this other data, but at least in the data that we have, like historical data sets, the only data is precisely the features that people actually wanna be representative with respect to. Now, for your point that some of these features may not be that relevant, obviously that's okay for the estimation algorithm, because if gender, for example, doesn't play a role at all, then the parameter for gender would just be 1, and then it wouldn't play a role in this product of parameters at all. That would just be the solution given by the algorithm that kind of fits these parameters. So I don't think it's an issue that some features may not play a role. This point about maybe there are other features that are relevant for estimation, but not for, but we don't want to be representative with respect to. That's a great point, and I can definitely imagine like collecting more data just for that purpose if this was implemented.
Thanks.
Other questions? If not, Ariel, I want to thank you very, very much for this. This is there's a lot that's very interesting about this, but what I'd say is most compelling to me is that I agree very much with your final slide. That it's really this is research that actually really matters for how we're doing democratic representation in the world. It solves a problem that kind of semi-critics like me of citizens' assemblies have had for a long period of time. And I think you're convincingly closing the door on that set of criticism. So I really want to commend you on that. And also very, very plainly and clearly presented. So thanks very much for the time you've given us today in your talk, for your willingness to meet with so many of our colleagues today as well. And thank you just for doing research that really matters. We're all the better for it. So I'll ask everyone to join me in giving you a really well-deserved round of applause. Thanks very much, Ariel.
Thank you so much. It was absolutely my pleasure, both giving the talk, chatting with you all, meeting with some of you. Thanks so much for the invitation.
Thank you very, very much. And thanks everyone for coming to this week's talk.